Alright, so in the same spirit as last video, we're still going to be looking at, well, honestly, just one more theorem, not so much as the same amount of theorems we had last time. And last time that's what we did. We went over Fermat, we went over Euler, we went over Wilson, and these are just basic theorems for modular congruences. Well, maybe the first time you see them, they don't seem so basic. And so in this video, there's only one really important theorem for us to go over today. And then in the next one, we might actually be able to move on to RSA. So first, before we actually start with the theorem of the day, I'd like to go over linear congruences in one variable, and you'll see that it's actually just a repetition of linear Diophantine equations in two variables. So let's see. The proposition is that if we let G be the greatest common divisor of A and M, then the linear congruence AX is congruent to B mod M has a solution if and only if G divides B. And if so, it'll have G solutions mod M. So to see why this has to do with linear Diophantine equations, we're going to rewrite it a little bit. Yeah, as I said, it's just a restatement. So we have that AX is congruent to B mod M, and that just implies that AX minus B is equal to MK, because that's the definition of congruences. And so that implies that AX plus M times minus K is equal to B. So once again, here, here I'm applying the definition. And then I'm just rearranging. So this is the linear Diophantine equation in two variables, right? We've got one variable x here, and I guess, you could imagine that either m or minus k is a variable here. You don't even have to worry about it being in two variables, but imagine that one of these is a variable, and then we'll only look for a solution for x. That's all that we're interested in. And so you know that that has a solution if and only if g divides b, where g is the greatest common divisor between a and m. So in this case, the variable would actually be minus k, since a and m would be the coefficients. Okay. So for the other parts, which is how many solutions there are mod m, well, we can again refer back to our linear Diophantine equations. And by the way, if you don't remember how these work, refer back to video 2, otherwise you might be a little confused here. So we know that from Diophantine equations, the solutions are the form x is equal to x0. Now this x0 is just any solution, it's some initial solution, times, plus j times m over g. And so j can be any integer, and so j are just going to range over the integers. And this we know is an integer as well, because g is a divisor of m, because it's the greatest common divisor of a and m. So we're basically just applying all the numbers that are a multiple of m over g away from x0. And so that's going to be all the integers of x that are going to fulfill our equation. But we're interested in the solutions mod m. So they're going to be x0, x0 plus m over g, and so on, till x0 plus g minus 1 over m over g. And note that I'm not going to go further, right? I'm not going to have x0 plus g times m over g, because that would just be x0 plus m. Let me just write that here. That would be x0 plus m. And that's just congruence to x0 here, because m reduces to 0 mod m. Okay? So that was just, one type of congruence that we might want to solve. And we're going to look at more complicated types of congruences if I still keep going with this after RSA, like quadratic congruences, for example. And this is just one example that might motivate the next theorem here. Well, first we're going to actually find x0 for this. Because, the generating solution x0 is actually really important, but we didn't bother to actually find it at all in video 2. I mean, we mentioned what the general form was, but that's all assuming that, we know how to get an initial solution. That might not always be super easy. So the way to do that in the general case is we're going to write a is equal to a prime times g, because remember g is a common divisor of a and m. M is equal to m primes times g. And the reason that we can write b is equal to b prime times g is that remember that there's only a solution if g divides b, right? So that's going to happen anyways in this case. So we'll be able to write b as a multiple of g. And then we do all that such that ax is congruent to b mod m, okay? So we can rewrite this, and we're going to rewrite it as a prime times gx is congruent to b prime times g mod m prime times g. So I've just plugged in these definitions here, and I've plugged them into here. And so that's going to be, I can do some reduction here. That's going to be if and only if a prime x is congruent to b prime mod m prime. Now the reason I can do that is because I've got a multiple g here, I've got a multiple g here, and I've got a multiple g here. And keep in mind, this is one of the theorems that I asked you to prove 2 videos ago. And it's just that when you have such a congruence like that, where you've got a common multiple in each of them, then it's equivalent to really just removing that multiple. And the other way around too, you know? I mean, that's why it's an equivalence. So since the greatest common divisor of a prime and m prime is 1, so for co-prime, then we have that a prime has an inverse mod m prime. Now this is, again, just the definition of inverses modulo m, right? That only happens when we have a greatest common divisor of 1, so when we're co-prime. So we know a prime has an inverse. So algorithmically, the way we can find the inverse is to first actually find s and t for a prime times s plus m prime times t equals 1. We know that such s and t exist because they're co-prime, right? And that's Bezout's lemma. And we can find those by using the Euclidean algorithm. And remember, you can do the Euclidean algorithm to find the greatest common divisor. But if you reverse the steps, you can find the linear combinations that get you to the greatest common divisor. So it would give us s and t. So then in that case, we're going to have a primes times s is congruent to 1 mod m prime. Now, why do we have that? Well, that's because we've got a prime times s minus 1 is equal to m prime times minus t. And see, I've just rearranged this equation into here. And so here, if I apply the definition of congruences, then I get exactly this here. And so we've just discarded the t because the t is the multiple that allows us to make this true. And so, you know, by the definition of inverses modulo m, it's a number such that when multiplied with what it's the inverse of, it gives us 1. It gives us a congruence of 1 mod whatever we're working in. And so in this case, that's going to give us that s is going to be the inverse of a prime to the minus 1. So algorithmically, that's how you find the inverse mod m of a prime. And so that's because, I mean, in the end, we want to actually find x0. So technically, our steps here are doable. We can use the Euclidean algorithm, then we'll get s, and then with s, you know, we know that's the inverse. And so therefore, I can multiply by this equation here by s. And I can multiply just here, obviously. I don't have to multiply there. And so I get a prime times s times x is congruent to s times b prime mod m prime. And so, of course, now I can apply this definition here. Because it's the inverse modulo m, I know that as is going to go to 1, so that's why it disappears here. And we've got x is congruent to sb prime. And so just haven't changed the right side here. And so now we actually have a solution, right? Because we've got a solution mod m. Remember, we're not trying to detail the solutions to linear Diophantine equations here, but only to the congruence. So, you know, in linear Diophantine, this would give us an infinity of solutions, which is fine. In our case, we just need one solution mod m. Well, mod m prime in this case. And so, you know, we've got x is congruent to sb prime mod m prime. And so we can just set x0 equals sb prime. Because keep in mind, if this solves the congruence mod m prime, it's going to solve the congruence mod m, because m prime is just a divisor of m, right? Because this explicitly only gives us a solution of x for when we work in mod m prime. But since m is equals to m prime times g, then it's also going to work mod m. Okay? Just to make that clear. Okay, so next. Let's look at some tools for solving congruences. Well, we'll actually look at them later. I was kind of just reading off the title here. And once again, that's what I was saying about quadratic congruences, for example. But one question we can actually ask now, and that we can answer, is that given that we have solutions to a lot of different congruences, right? So I've got a lot of complicated congruences maybe, and I want to find some kind of common solution to them. And so maybe I know the tools to solve each of these congruences individually, right? And so then I'll just get, you know, individual solutions like x is congruent to a mod m, and then I'll get, you know, some solutions for the other ones that are analogous to this. But we want to combine them to get one common solution. And so that's exactly what the theorem we're just going to look at now is going to work. And so, you know, in other words, it's just how to solve a system of congruences. And the system is going to look like this in the general form, where once we've solved each congruence individually, we've just got x isolated and it's congruent to some constant mod some constant, right? So that's just for our different modulars. So we can have different numbers here for the m's, or we can have the same. And but the same is not going to really give us a solution most of the time. And then we have different constants here. And so, yeah, we can find a common solution with a Chinese remainder theorem. And we might actually first ask ourselves, before we even find it, if it actually exists. So let's look at the Chinese remainder theorem in detail. So the Chinese remainder theorem says that if the moduli are pairwise coprime, so by the moduli I mean all the m's that we had in our system, so what pairwise coprime means is that we've got that the greatest common divisor of mi and mj is equal to 1 if I is not equal to j. So what that means is if I pick any two moduli in my set of all moduli, then I'm going to know that they're coprime. But that doesn't necessarily mean that all the moduli are coprime to each other. It just means that they're pairwise coprime. So it's a bit of a weaker statement, well, in some cases stronger because it allows us to do more things, but it's not as specific. So then the system's going to have a unique solution, mod m1, m2, all the way to mk. That's what the theorem says. And we're going to look at what that unique solution is. Otherwise, it would be a little weak if it just told us it existed but didn't tell us how to do it. Alright, so let's look first to show that this solution is unique. And we'll look at existence afterwards. So first we're going to have to prove a lemma. And the lemma is that if a1 divides b, a2 divides b, all the way to an dividing b, and those divisors are pairwise coprime, then, so the divisors by that I mean the a's, then a1 times a2 all the way to an divides b. So just note, these a1s and a2s here, they're not the a1s and the a2s from our system. I've just used the same symbol, just to avoid confusion. So let's look at the proof of that lemma, and we're going to do it by induction. The harder part actually in this induction is the base case, and once we've done that, the induction itself is pretty easy. So let's look at the base case, which is going to be n equals 2. And so we're just going to note that the greatest common divisor of a1 and a2 is equal to 1, right? I mean, that's the assumption here. We're saying the divisors are pairwise coprime. And so we just apply Bazoo's lemma to get a1 times s plus a2 times t is equal to 1, okay? And we know this exists. Now we're also going to note that b is equal to a1 times k1, because a1 divides b, right? So there's some integer that I can multiply a1 by to get b. And similarly, there's some other integer I can multiply a2 by to get b, because a2 divides b. So now let's consider this big number here. So let's look at this first, okay? So we've got this number, and it might seem a little random at first, but it's carefully chosen so that we get a nice resolution in the end. And mainly what we want to note is that we've got a1 and a2, and they're just multiplied by some number here, okay? And what we're going to show is that this is going to be equal to b, so that we know that a1, a2 divides b. So if we rearrange this a little bit, okay, I can take a1, I can take k1, and so I get a1, k1. And so what I'm going to be left with is going to be the a2 times t, which is here, okay? So that's why I put that here. Then I do the same for a2 and k2, and I'm going to be left with a1 times s. It's getting a little messy, but whatever. And so we've got a2, k2 times a1 times s. So that's just my rearrangement. And so now what we're going to note is that we have that b is equal to a1, k1, and it's also equal to a2, k2. So this here goes to b. Well, this here is b, and this is also b. So I can factor a b out of this whole thing and have these two as a linear combination of each other. So I've got b equals a1s plus a2t, okay? But now, a1s plus a2t we have right up here is equal to 1. And so that's just going to give us b in the end. And so we've got that a1, a2 times some number is equal to b, and so that gives us that a1, a2 divides b. Okay, so that's just the lemma. We actually have to prove uniqueness now, if PowerPoint will work. Okay, so let's continue the induction. Oh yeah, because we actually haven't proven the lemma, we've just proven the base case. So we actually have to continue the induction first. Let us assume that the lemma is true for n is equal to L, okay, and we're going to consider n equals L plus 1, so just standard induction here. So we've got that a1, a2 all the way to al, so multiplying all these together, we're going to divide b, and that's just what the lemma tells us for the hypothesis, for the induction hypothesis, okay? Now we have that a1 times al plus 1, the greatest common divisor of a1 and al plus 1 is the same as the greatest common divisor of a2 and al plus 1, and is the same as all these guys here with al plus 1, and it gives us a 1, because everything's pairwise coprime, okay? And so from a proposition in video 2 that you might remember, when all these guys have the common divisor are the same, when they all give us 1, it's all these greatest common divisors are 1, but we have a common term at the end like this, then I can just multiply all these guys and still get 1, okay? So this is what we have here, and you can always refer to video 2 to look at the proof again. So that's going to be a useful little fact. Because now, well, we've got that AL plus 1 is pairwise coprime in some sense with this big number here, A1, A2, all the way to AL. So what we could consider is just consider, well, this as one big number A, I guess. Okay, and I guess you could call it A1. And we'll call AL plus 1, we're going to call it big A2, okay? And so we've got that A1 divides B, and A2 divides B. And so we want to show that A1, A2 divides B. But we're given that their greatest common divisor is equal to 1, and so these guys are pairwise coprime. And so by the base case, because we did the base case already for two numbers, then that tells us that A1 times A2 is going to divide B. And so re-expanding from our definitions here, then we get this whole thing divided B, which is exactly what we need, and that completes the induction. Okay, so now let's actually finish proving uniqueness using the lemma. And we'll need PowerPoint to load. Okay, so let's finish that off. So let's assume that we've got two solutions. X is congruent to Y is congruent to A1 mod M1. X is congruent to Y is congruent to A2 mod M2, and so on for all the moduli, right? So X and Y are our two solutions. And so we're going to have to prove that they're the same modulo M1 times M2 times M3 all the way to Mk. Well, we have that M1 divides X minus Y, we have that M2 divides X minus Y, and we'll have that M3 divides X minus Y, and so on. Now the M's are pairwise coprime, so the lemma can be applied to see that actually M1 times M2 times M3 all the way to Mk is going to divide X minus Y. And so that's why we needed our lemma, is to get this. And so now, this just translates straight away to a congruence, and we've got that X is congruent to Y mod M1, M2 all the way to Mk. And so that shows that X and Y are the same mod M1, M2 all the way to Mk, so that we only have a unique solution mod M1, M2 to Mk. Alright, so now we actually want to prove existence and see how we might actually get a solution. So we're going to claim that the solution is actually expressible as the linear combination of the AIs, so those constants that we're comparing to, okay? And so we're going to say X is equal to big A1, just some coefficient here, times A1, plus big A2 times A2, plus so on, plus AK times AK. And so what we want to do right now is figure out what these A1s and A2s are, and prove that it actually works so that we actually complete the proof of existence. So if we think about it, one way we'd actually be able to pick those A1s and A2s and AKs is exactly analogous to looking back straight at the system of congruences and seeing what kind of behavior we want. So the way we're going to pick them, right, for it to work, for it to work, we're going to need that for all the AJ, well, big AJ, where J is not equal to I, we're going to need them to be congruent to 0 mod Mi, okay? And so the reason we want that is that, say I'm considering the second congruence in my system, right? So I'm considering the one with M2. Well, if all A1s and A3 and all the way to AK is congruent to 0 mod M1, then all these guys are going to disappear mod M2, sorry. And so in our congruence, we're going to be left with X is congruent to big A2 times A2. And so that means that the final restriction we need is that AI is congruent to 1 mod Mi. So that in the end we get X is congruent to A2 mod Mi. Exactly. And it'll be the same for all of them. Okay, so let's see how we might actually do that. So first we're going to define these numbers, which we're going to call n's. And so n1 is going to be just the product of all the moduli except m1. So we're going to have m2 times m3 all the way to mk. n2 is going to be similar. It's just going to be m1 times m3 all the way to mk. And so we just removed m2 this time. And we do the same for all of them, so that ni is m1 times m2 all the way to mi minus 1 times mi plus 1 all the way to mk. So this is just to, normally we'd have the mi here if we had a full product, but we're just removing that for this ni. Okay, so remember that the moduli are pairwise coprime. So that's just what this text is saying. And so that means that we have, once again, by the theorem that we proved in video 2, which would give us that we have a common term at the end of these greatest common divisors, and we can just multiply the first one to get the same thing. So that means that this whole product here with mi is equal to 1, okay? And so I note, that I didn't include mi because, of course, the greatest common divisor of mi with mi is not 1, it's mi. So we're only interested in this product without mi, okay? And so what that gives us is, well, by definition, this here is ni. So we've got, I'm trying to write ni. Yeah, so we've got that ni and mi have greatest common divisor of 1, not just and so GCD ni mi. We need some kind of equation here. Okay, so that's what we get. Let me just rewrite it here for our annotations. Okay, so therefore, that means that ni has a multiplicative inverse mod mi, right? Because, well, it has greatest common divisor 1, and so by the way multiplicative inverses work, or inverses modulo m, maybe that's, you prefer me saying it like that, then ni is going to have to an inverse modulo mi. Okay, so let's keep that in mind, and let's continue the proof in this last slide. So now we're going to let hi be ni to the minus 1, okay? So hi is going to be the inverse modulo modulo mi of ni, okay? And so we're going to let ai equals hi times ni, okay? And so we're keeping ni and hi reduced. So then ai is congruent to 0 mod mj, and ai is congruent to 1 mod mi. Now why is that? Well, mod mi, we've got that these guys multiply to give us the multiplicative inverse, and so by the definition of inverses modulo m is going to give us 1, okay? So that's how we get this one. And then for mod mj, well, ni is going to include all the mj's, you know, they're inside ni here. And so that means that we're just going to get 0 because it's going to divide ai. So that's exactly the type of behavior we wanted. And so that completes the proof. So, you know, let's actually do an example of this to actually get our hands on it. So let's, okay, here. So we've got this congruence here. We've got that x is congruent to 2 mod 3, and you know, maybe this was a more complicated system first, but we managed to reduce each individual congruence to this simple solution for each of them. So we've got that x is congruent to 2 mod 3, x is congruent to 3 mod 5, and x is congruent to 5 mod 7. And so we want to find a common solution for all of these. Well, let's note that n1 is going to be 5 times 7, so I remove 3 and I only consider these two. Okay? And so that's 35, and that's congruent to 2 mod 3. Okay? So how do we find the multiplicative inverse? Well, for this one it's pretty easy. We'll just know that 2 times 2 is 4, and that 4 is congruent to 1 mod 3. Otherwise, you could use the Euclidean algorithm to find the inverse, like I've mentioned before. Okay. In this case, it's pretty easy. So n2, we remove 5, we get 3 times 7, that's going to be 21, and that's congruent to 1 mod 5 because 5 divides 20. And then in this case, well, the multiplicative inverse is super easy. Well, the multiplicative inverse of 1 is just 1, so that's really easy. And then similarly for this one, we're going to remove 7, and we're going to have 3 times 5, which is 15, and 7 times 2 is 14, so this is congruent to 1 mod 7. And then once again, this is congruent to 1, so the multiplicative inverse is also 1. Okay, so now we've got that x is congruent to h1 times n1 times a1 plus h2 times n2 times a2 plus h3 times n3 times a3. So that's how we described our solution earlier. Now that is going to be congruent to 2, because we've got 2 here, times 35. And you know, I've written 35, but I could have actually reduced it to 2 here. Plus 1 times 21 times 3 plus 1 times 15 times 5. Okay? And so, you know, if you do all those computations, you get 278, and that's going to be congruent to 68 mod 105. And so that's exactly our solution. It's going to be any integer which is congruent to 68 mod 105 is going to be a solution to our whole system. Okay, so let's look at an important property of the solution that's actually going to help us understand the totient function that we mentioned last video. So I'm just going to wait for, oh, yep, I'm going too fast. So let's let x be the solution to the system of congruences that we just presented, okay? And we're going to say that the greatest common divisor of x with m1 times m2 all the way to mk is equal to 1, okay? And that's going to be if and only if the greatest common divisor of ai and mi is also equal to 1. I should have put that as well. Okay. So these are equivalent statements, and that's what we're going to try to prove. And that's gonna give us a nice way to think about the Euler totient function. So let's look at a proof, okay? Well, if x is co-prime to the product of all of these mi's, so first we're doing one direction, right? We're imagining this, and then we're going to show that it implies this, okay? So if x is co-prime to the product of all the mi's, this is just a more concise way to write this big product. Then it's going to be pairwise co-prime with each mi, right? Now, why do I say that? Well, let's assume it wasn't pairwise co-prime with each of the mi's. So say, for example, the greatest common divisor of x with, I don't know, m2 is going to be 4. Well, then if I take the whole product of them, then it's going to be divisible by it's still going to have a divisor of 2. And so it's not going to be coprime to the whole thing. So it at least needs to be pairwise coprime with each of the mi. So since we have that x is congruent to ai mod mi, because it's a solution to our system, we have that the greatest common divisor of ai and mi is going to be the greatest common divisor of x and mi, right? These guys are congruents mod mi, so we're going to have the same greatest common divisor. And so that's going to be equal to 1. And so for the converse, let's assume the greatest common divisor of ai mi is equal to 1 for all I. Well then, since x is congruent to ai mod mi, we're going to have the greatest common divisor of x and mi is equal to the greatest common divisor of ai and mi, which is equal to 1, holding for all I. So that works as well. So it's the same as this equality, we've just done it the other way around. And so we get that the greatest common divisor of x with mi times m2 all the way to mk is going to be equal to 1. Oh yeah, this is because, keep in mind, here I've shown that the greatest common divisor of x with mi is equal to 1, so it's pairwise coprime of all of them. And then we can apply our lemma from earlier to show that it's pairwise coprime, well, that is coprime to the whole thing. Okay. Well, not our lemma, sorry, our theorem from video 2. So now let's use that for the Euler totient function. So what we want to know is what is the number of x that are coprime to m1 times m2 all the way to mk. So we're going to use our above result, and I've just rewritten it out here, so in case you don't remember it already. If and only if, and I should write that again, if and only if this is equal to 1, okay? So we're going to use this, and we're also going to use the multiplication principle, okay? So phi of m1, m2 all the way to mk. Well, we're asking what are all the numbers smaller than m1, m2, mk, so all the numbers mod m1, m2, mk, that are coprime to m1, m2, mk. And note that we've exactly described these numbers. We've said that, if x is coprime to m1 and 2 mk, then we've got this being true as well, and actually it's equivalent. So what we can actually do, this reduces to the problem of asking, the number of choices we have for a1 being coprime to m1, then the number of choices we have for a2 being coprime to m2, and so on. Because keep in mind, we need all the ai's to be coprime to all the mi's. So we need to look at all the different choices we can have of that. And then we apply the multiplication in principle to combine all of these. And so that actually gives us exactly a formula for phi. So we have that phi m1, m2 all the way to mk gives us phi of m1 times phi of m2 all the way to phi of mk. If the m's are pairwise coprime, that you definitely need that. This isn't true for all the m1, m2, mk's, right? Because if we're not pairwise coprime, then we don't actually get a solvable system of congruences, and so we can't apply this rule here, because this implies that x is a solution to the congruence. Okay, so how does this help us actually understand it for any n, right? Because here we need these guys to be coprime. Well, note that by a fundamental theorem of arithmetic, then we have n is equal to p1 to the e1 times p2 to the e2 all the way times pk to the ek, where all these p's are primes. And this is going to help us because we have the greatest common divisor of pi and ei is pj, ej, okay? Oh, sorry, the greatest common divisor of pi, ei with pj, ej is going to be 1 for all coprime because of our primes, and primes are obviously coprime to each other. Well, these are prime powers, but this also still applies because the only factors they have are primes anyways. So now we just need to find the phi of p to the e. And so phi of p to the e is going to be the size of the sets, including the elements x, where x is smaller or equal to 1 and bigger or equal to 1 and smaller or equal to p to the e. And we need that the greatest common divisor of x with p is equal to 1. Okay? Because keep in mind, if the greatest common divisor of x and p is equal to 1, then we can apply that theorem from video 2 multiple times to get that the greatest common divisor of x and p to the e is 1. So we can apply some intuition to see that that's going to be p to the e minus 1, p to the e minus 1 times p minus 1. So why is that? Well, the way we can get that is to note that if we were just considering p to the 1, right, well, all the numbers smaller than p would be coprime to p, right? That works. Now, let's say we were considering p squared, right? Well, we have all the numbers smaller than p are coprime to p to the squared, right? We also have all the numbers that are between p squared. So this is not a minus, so I'm just mean between. I don't really have a notation for that. 2p, sorry, not p squared. And I can do the same for 3p, and I can keep going until I get to p squared. And keep in mind, p squared is just p times p. So what that means is I can consider, well, I can consider all the p minus 1 smaller than p, the p minus 1 between p and 2p, the p minus 1 between 2p and 3p, all the way to the p minus 1 between p minus 1 times p and p times p, which is p squared. So what that means is the amount of intervals that we have here, well, in this case, we have exactly p minus 1 intervals. We have exactly p intervals, sorry, which is p to the 2 minus 1, right? That gives us p. So now this is kind of a mumble jumble, but you get the idea. And so we have p of these intervals, and in each of them we have p minus 1 coprimes. So in the end, we're going to have p to the e minus 1 times p minus 1. So it's like splitting between, basically you take all the numbers that are smaller than p to the e, but you remove all the ones that are multiples of p. Okay? Alright. And so I can just rewrite that a little. I can, factor out a p here to get p to the e, and that's going to be p to the e times 1 minus 1 over p. So now we're not speaking in integers anymore, because this is not an integer, obviously. Hence, 5n is equal to n times the product from where p divides n of 1 minus 1 over p. So here I've just applied this here, right? So I've multiplied all the ones what we have, so that in the end I get, for this n, for example, I'd get p1 times e1 times, this thing here. I'll do a big pi for product, I guess. Then I'll do p2 times e2, well, to the e2, sorry, times pi again. And, we'd keep going. And in the end, that gives me p1 times to the e1 times p2 to the e2. You can combine those together to get n exactly, so that's the n we have here. And the other ones are going to combine in one massive product, where we're going to consider all the p's that divide n, so all the prime divisors of n. And that's just going to be the product of that term that we have inside here. And so that's an explicit way to compute phi of n. And so, I'll leave you to try and compute some of those yourself. But that's going to end this video. In the next video, we're probably going to be looking at RSA. Well, we're definitely going to be looking at RSA. And we might be looking as well at how to do some of the methods that you need for RSA as well, which are kind of sub-methods, I guess. And that's just going to be, in general, nice applications of all the theorems we've been looking at so far. Because we haven't been really doing much applications. It's been mainly theory here. Except for the Chinese Remainder Theorem, I guess, that helps us compute the totient function. Alright, and that's it for today.